Good morning, everyone, and thank you for joining. Before we begin, just a few housekeeping rules, please. If you may, just please keep your microphones muted during the presentation, and you are welcome to post your questions in the chat box. There is a Q&A chat box, so if you can just please post them in there. You will also have, again, a dedicated Q&A session at the end of the session. Welcome. Um, And then for common questions as well as frequently asked questions, there will be copies of this presentation as well as this video recording that will be provided to you in about 2 days post this presentation. You'll also get a certificate of attendance. There is one slide that will come towards the end of the presentation where you will be presented with a link or a QR code that you can just scan in order to obtain your certificate of attendance. It is my pleasure to welcome you here in today's webinar, hosted by the Engineering College of Science and Technology. Thank you all again for taking the time to join us for this session on fundamentals of power systems. Power systems are central to electrical engineering, forming the foundation of how electricity is generated, transmitted, as well as distributed. Today's session will provide valuable insights into the core principles. Understanding these fundamentals is essential for every aspiring and practicing electrical engineering professional. Today's session is designed to provide foundational insight into these key concepts within the power systems, and we trust that the session will be both informative as well as engaging. My name is Busisiwe Matehu, and I am going to be your host for today. It is also my pleasure to introduce our presenter, Mr. Samkelo Nene, who will be taking us through today's session. Um, Samkelo is a candidate engineering technologist who's registered with ECSA. He also holds an honors degree in electrical power engineering. He's recognized for his academic excellence and leadership and was inducted into the Golden Key International Honor Society. He's also contributed to the sustainable energy initiatives through his work with the South African National Energy Development Institute. He's also one of our esteemed lecturers here at the Engineering College of Science and Technology. Samkelo, over to you.
Hello, thank you, Wusi. Hello, everyone. I hope you're good. Let me just take control of the slides so we can start with the session. So, I'm not sure if on your side are able to see the slides moving. Wusi, please give me a sign.
We can
Oh, they
see
are
it.
moving. Okay,
Yes, they are
thank you.
moving. Thank you.
Thank you. So today, basically, we'll just cover one of the electrical engineering foundations, which is fundamentals of power system. So whether you are designing an infrastructure or or managing power flows, it's very essential to understand how electricity flows and stays stable. So on your screen, you'll see a list of contents which sort of touches on what we'll cover today. So we will start with the foundations of electrifications. Uh, so basically the early electrification side, just bear with me. I just want to make my screen big so that I can able to see. Okay. And thereafter, the first part, which is more of like the history of electrification, then we will jump into the core elements of power systems. So that's from the generation to the transmission of power to the distribution and then the load, which is the end receiving part of the electricity uh, network. And thereafter, we'll then just quickly go over some of the case studies, particularly on our history when it comes to the electricity grid. So let's jump into it. Uh, I'm sure we all know about Thomas Edison. Thomas Edison. We have heard a lot about Thomas Edison. So if we just go back into the history, uh, obviously today we know the power system as being AC. You know, if we were to ask anyone why is the power system is AC, and also while I'm still there, just feel free to just drop comments and question as we go along. Normally, when we ask people why is our system AC, they will tell you it's because it's cheaper, it's because you are able to transfer electricity, over long distances. Uh, and most people you'll find, or some people you'll find, they're not even aware that at some point electricity was transferred, or rather the system was DC. So initially, the power system was DC, which was sold to or in this to mining and industrial um, companies for use before it was even used for residential use. So Thomas Edison was one of the first people who designed a power system which was DC. However, it could only transfer electricity over a short distance due to the voltage levels, which were low, and also the resistive losses were very high. So it wasn't as efficient as one would want it to be. So before, it got to be AC, at some point it was high voltage. So you hear now and then people will talk about the break-even point. At what point is high voltage um, uh, DC uh, system advantageous? Obviously, there'll be a range about 500 to 600 kilometers. Yeah. So that's about it regarding the story with Thomas Edison. And one of the facts, or one of the interesting things really I found was that the New York City subway system, which happens to be the largest, one of the largest subway systems in the world, runs on DC power system. I think that's very, very amazing. And one of the reason why is that is because it employs the TC motors, which are renowned for its efficiency when it comes to heavy loads, as they have high torques. Um, and also in New York, back I think until 2007, you'll find that there were many residences that were powered with both DC and AC current. But however, what would happen is that some outlets in the apartments were DC while others were AC. So and they look the same. So people will make mistakes connecting AC loads onto DC outlets. Hence, around 2007, they had to then change outlets and also to make sure that everyone is powered using AC system. So what led to the development of the three-phase AC system was obviously the invention of the likes of transformers, um, which made it easier to transport electricity over long distances. There's a picture there which shows Thomas Edison first hydroelectric power plant. So you'll find that there were two. So there is this one, the hydro. There is also the Pell Street one, which originally his first power plant, but this is his sort of like first hydro power plant. Basically, it employs uh, the gravitational gravitational force and kinetic force of water basically to drive turbines to produce electricity. And one of the early so this was a more of like an experiment. So from Misbeck to Munich, Germany, they built a DC system, to transport electricity. It was about 57 kilometer, not very long, but at the time it was the longest. And if we were to compare to nowadays technology, obviously today with the invention of like power electronics, we are able now to use DC again over long distances. For example, if you compare to the current longest DC line, which is Changchi Gokhan, it's not even just high voltage, it's ultra high voltage direct current line, which is about, I think, more than 3,000 kilometers. So you see that with the advent of semiconductors, power conductors, even high voltage DC current system are also, developing. So this is the station I was referring to, that the Pell Street station, which was the first one that Edison built, and thereafter, I think, few weeks or few months, he then went on to build the hydroelectric one. And then the Great Barrington, Massachusetts. So this was the first full AC power distribution system. Okay, and you see next to the Great Barrington electrification picture, there is a picture of a transformer. So at that point, they were still trying to to figure out, transformer, um, putting transformers basically. And if we go to the next page, okay, I think it will be after this one, we will come across one of the pioneers when it comes to AC system. I know one will think of Nikola Tesla, which sort of developed the induction motor, but when it comes to the transformer, it was William Stanley. So I think we'll come across that just now. Um, and then another exposition, which was also in Frankfurt, to see again, this is Germany again. Germany has been at the forefront of transmission line. So this was another transmission line, but this is not DC as the one they did from Misburg to Munich. So this was from uh, Frankfurt to Laufen. This was a three-phase, the first three-phase sort of a demonstration. So you see, as we move from the 1880s to 1890s, we start to move from DC to AC, since we start to see that with AC we're able to transmit the voltage at over long distances rather. So here's William Stanley I was talking about, one of the people who helped to develop. Obviously, there were people already who started experimenting with transformers, but he helped to then develop the transformers, which was used at the Great Barrington, um, uh, Massachusetts. And on the right, we see Nikola Tesla, who invented AC induction motors. Obviously, if you were to compare the both transformers dealing with stepping up, uh, basically leveling voltage, whereas motors, which sort of like at the end when it's come to like load, industrial load, and so forth. So the invention and development of these both components really help when it comes to implementing AC systems. So AC system, DC motor, one could answer, what's the difference? They all look the same, even they're covering. You find that as much as they look the same, first of all, it's the current that they're using, and secondly, the application. You'll find with AC system that they're used for control speed. For example, if you think of pumps and fan, they're very good with that. And then DC, if you wanna, vary the speed in terms of like robotics and other battery powered devices, they're very good with that. Okay, so now we're at the point where the power system, this is early 1900s, is now is AC. But remember, before it was DC, so it means we still have DC loads. So with at the time, they then had to come up with conversions. When we think of conversion in nowadays, we think of your transistors used in power converters, which is what we use in now, or in the time and age. But back then, they had to then develop arc rectifier, mercury arc rectifier, and rotary converters, to make sure that the DC loads are serviced as they were before the ACES system was implemented. So these are some of the semiconductors that I was mentioning to the field the field transistors, which are used in power converters to convert DC to DC. Obviously, if we want to convert or rather transmit voltage at a higher voltage, we will need then to step it up, step up um, converters. Whereas with AC, we use a transformer to step up or and also to step down. With DC, we then use converters, boost converters, buck converters, and so forth. Obviously, this development of semiconductors led to obviously more advanced development in terms of like um, so after the development of conductors just to switch, because the switching was to bring flexibility, and thereafter we then had to go to more advanced conductors in terms of like communication and monitoring the grid. So the development of semiconductors has brought value to the grid. So that was about it regarding the history. I took so long. Anyway, moving on to the power system component. So this, in a nutshell, is a sort of a power grid. We do see generation network connecting to the transmission network, to the distribution network. Obviously, the voltage changes from the generation is medium, then step up to to high voltage for efficiency to reduce losses. Then again goes back to distribution, which is a lower voltage to then supply the load. So starting with the generation network, there are different types of energy that are used when it comes to generation of electricity. There's a picture there you can read bio, coal, and so forth. Um, Yeah, we will touch on those as we go. Um, as I've mentioned on the previous slide, one would then ask then why voltage or why electricity is generated at a medium voltage and then transmitted at a higher voltage, yet distributed at a lower voltage? Why can't be the same voltage? I think we also touched on that on the history regarding the resistive losses. And also the reason why a generation is at a medium voltage is because we are trying to make the most when it comes to efficiency and also when it comes to insulation requirement. For example, if we are transmitting at a higher voltage, for example, for transmission network, is done at a higher voltage because we are trying to avoid losses. Uh, if you look at your sort of like towers, you'll see outside if you're driving, normally you see towers, with wires. That's sort of our transmission network that at the top and also between the wire there is air which sort of provides insulation. Uh, so you ask then why don't we use high voltage when it comes to generation? So when it comes to generation, that's underground, and to insulate high voltage underground, that it's an art of its own. For example, underground cables that are high voltage, they have to be insulated in different layers, and that's also not cost effective. Hence, it's done at a medium voltage to ensure that it's not low voltage, also not high voltage, to ensure efficiency and also to ensure that insulation requirements are met. And then they obviously, when it comes to building a power plant or generation plant, there are factors to be considered. You have to consider environmental factors in terms of pollution, greenhouse gases. You have to consider economic factors and also resource availability. You'll find most of our coal power plants, especially in South Africa, since the majority of our electricity come from coal, you'll find that they are based near coal mines so that it's easier to then transfer the resources. So this is an example of a thermal power plant. So a thermal power plant uses a fossil fuel, whether it's coal or gas, which then it sort of acts function as a heat engine that drives steam turbines, which then rotates generators to generate electricity. And then we move on to hydro. Hydro is uh, falls under the renewables. So on the previous slides, you see that there's sort of separation. On the right, it's the non-renewable, and on the left, it's the renewables. So renewable, when you say renewable, they replenish, they're also clean as compared to fossil fuel based generation. So power plants, a hydro power plant, basically it employs the gravitational force of water. So there's a high reservoir and the low reservoir, gravitational height, kinetic energy, the water goes through the penstock to drive the turbines, which in turn rotate which in turn rotate the generators, which produce electricity. So one will ask then, uh, what is the difference between conventional hydropower and pumped hydro storage? I'm sure you've heard about pumped hydro storage. I'm not sure if there's anyone who would like to answer that, the difference between a conventional hydro. So a conventional hydropower, basically it will use water from a flowing river, a naturally flowing river. A pump storage, in essence, is what you see, two reservoirs, so water going back and forth. I'm not sure if there's anyone who wants to comment on that. So on this slide, these are two of our pump storage, one in Drakensberg and the other Palmit pump storage. These are ESCOM pump storage, which supplies our electricity. So with pump storage, basically, if you look at South Africa, I believe the last time I checked, we are classified as one of the semi-arid uh, region. So we don't have much water, like some of our neighboring countries. So we can't employ your conventional hydro like river flow. So what we do then, we then build pump storage. So pump storage is sort of like bidirectional. So when we generate power, we let the water flow down from the high reservoir to the low reservoir, and that's during peak hours basically, because they are used for peak hours when there is so much demand that even our coal plants can't manage. Then we then bring in pump storage to sort of help during the peak hours. So what they do, they let the water run down the pipe to drive the turbines, in turn to rotate the generators to make electricity. And then at night, when there is no demand, when everyone is asleep, then we pump them up the penstock back to the upper reservoir, since electricity is cheaper around that time. So basically, sort of bi-directional. It helps especially for a country like ours, which does not have that abundance of water. And then the next one is wind. So wind employs the kinetic energy of the flow of air uh, to drive the the turbine, the wind turbine. So you find turbine being part of these plants. So they are what we call prime movers, basically. Prime movers, they help to convert the mechanical energy into electrical energy by driving the generators. So for example, in this picture, we employ gearbox. Why? Most people ask, why are we using gearbox? Why are we not connecting the turbine directly to the system? Because, they are synchronous, they are unlike your solar panels, which are static. Why don't we connect turbine to the system? And feel free to answer, but just to quickly go over it, so traditionally, gearbox is employed since uh, if we were to connect directly, we'll have to have a massive generator, you know, to to connect with the rotor blades, turbine, the wind turbine, to get a sufficient torque. Whereas with the gearbox, we are able to have low speed shaft and high speed shaft, to work with the ratios to increase speed and so forth as required. But with obviously with the advent of the um, direct drive generators, now we're able to connect a generator directly to the grid to the wind turbine, but those are quite expensive at this point. Not every country can afford it. And then solar plants, which is also renewable, basically converting radiation from the sun using semiconductors into direct current, which is then inverted to AC to supply load or to connect to the grid, or we can then take the direct current produced from the solar panels. Obviously, we'll have to convert it or stabilize it. Then we can store it on the battery storage, which is DC. So there are also challenges when it comes to rooftop solar panels, which we have in our houses as compared to solar plants. Also, solar plants, they also have their own challenges when it comes to like transferring that massive power of renewable across the grid. But the interesting part is the rooftop solar plant because when we went over the picture of the whole grid, when it comes to distribution side, where we are as residents, as load, you'll find that the voltage is very low. So sometimes high penetration of rooftop solar panel can lead to over voltage, which is not good, especially at those receiving nodes. And then biomass. Biomass is not prevalent. Even if we were to go and check our mix, our energy mix, our electricity mix, in most countries, even if we were to check the global mix, biomass, when it comes to the mix, is not as prevalent as compared to your renewables, the solar, wind, even coal and nuclear. But Brazil, you find Brazil that a majority, a big part of its energy mix, electricity mix comes from biomass. So one of the reasons why it's not prevalent when it comes to most part of the world is because they're very expensive. The power plant itself very expensive to build, and also it still faces criticism when it comes to its carbon neutrality, since you are burning wood, you are burning chips, you are burning waste. So there's still questions around its carbon neutrality and also is it really a renewable? So hence there's that hesitation when it comes to the uptake. Whereas with Brazil, obviously it uses policy, to encourage the uptake of biomass. So this is our generation network in South Africa. So those dots that you see on the map, those are power plants, and you see that there's sort of a concentration towards the north. So the Gauteng, Mpumalangas, that's where you find majority of power plants, which are coal power plants. As I've mentioned, they have been placed strategically near coal mines so that it will be easy then to transport the fuel to the coal power plant to burn it to drive the steam turbines. And this is also a map of our peak power station. As I've mentioned, one of them is pump storage. So we have your normal or your base power station, which runs day to day. Uh, it supplies, so it meets the demand on day to day, like minutes, hour by hour, whatsoever. And then we have peak power station, which only comes uh to rescue if your base power station, your coal, your nuclear cannot meet the demand. So this obviously during the evening when everyone is back from work and everyone wants to, plug on, then we bring on the peaking power station, your diesel power station, your pumps storage power station. Diesel are quite expensive. That's why I only bring it during those time. Yeah. And then this is our transmission network. So you see lines moving from one province to another. Um, from provinces to another province, from a city to another city. I believe we are all from South Africa. For those who are outside South Africa, I'm not sure if they're familiar with the word provinces, which is sort of like state, basically, moving one power from not state. I'm thinking of United States now, but sort of like, from one major region to another major region. Obviously, it differs across the world. We use province as some part of I think Asia do also use provinces. So yeah. Anyway, that's not the case. So the case is you see lines running across all these lines running across the country. These are transmission lines transmitting electricity, and you see they're congested here around Gauteng. So this is where we are, basically where I am, and also ECSTE is based in Midrand at the central of Gauteng. You see congestion here because there's so much demand. As much as Gauteng is like our smallest province, it happens to be our economic hub. So there's a lot of demand of electricity around Gauteng, as you see with the congestion of transmission line. And also the power plants are not so far away from Gauteng. We have power plants here, and also Pumalanga, which is not so far away from Gauteng. Hence, you see this congestion. So these pictures, or these figures, is the one that also was shown under generation network. You can find these uh, at ESCOM's website, our utility basically for electricity. Um, So if you were to look at the summary of the critical components when it comes to the transmission network, so these were taken from one of the development plan of our transmission company, which in the meantime is sort of in between ESCOM and being independent. So it shows some of the critical components, some of the critical components of the transmission line. The first being the power lines, which transmit the electricity, then transformers, which deal with voltage leveling, and then reactors, which deals with obviously absorbing reactive power to avoid um, uh, voltage changes or over voltage rather, and then capacitors which supplies a reactive power in case there is a shortage in voltage. So it's very important to keep voltage at a level that is uh, that is required. So for example, with transmission line, I think it's transmission line run on 765 kilovolt transmission line. That's the rating. So it's very, very important. We will touch on that as we go along when it comes to keeping the grid stable. We'll touch on the importance of voltage, stability, and frequency as well. So this is your typical transmission line. Um, uh, the first figure on on the left shows the AC power line versus the DC power line. AC, you see it has three wires. Uh, Three wires, three-phase wires, DC2. Um, and we did touch on the break-even point. So normally AC is is recommended since it's cheaper to run over long distances when you compare in terms of like the components. For example, the major components when it comes to AC is transformers. When it comes to DC, it's converters because they sort of, fulfill sort of the same function because with AC you need transformer to sort of to levelize voltage to change from one to another. With DC you need converters. Converters are way more expensive as compared to transformers. But at some point again there is that break-even point. So above 600 kilometers, that's where DC high voltage DC lines tend to be favorable. And on the left, you see the transmission line. There's quite a lot happening there, to be honest. So we see the balls, which are visibility balls. Normally, they're orange, yellow, different colors. So not really electrical, but just to help in terms of like low flying aircraft and helicopters not to come into collision with the transmission network. Obviously, if they fall or if they crack, that implies infrastructure that is aging, and that's not good because we need to have it there to protect uh, the transmission network. And then we see a shield wire going over the 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 conducting wires. So the shield wire obviously protects the wires from lightning. And also you'll find that nowadays you'll have sort of like a communication wire going through the shield wire to sort of provide communication to the control center as to what's happening in substation and also in the transmission network. So yes, and then after transmission line, we have the shunt reactor, power transformer, capacitor bank. As I have explained, the reactors they assist when there is over voltage to absorb reactive power, and then power transformers they levelize the voltage. Capacitor banks they help when there is under voltage to supply reactive power. So reactive power, as much as we say it's not a real power, it assists when it comes to voltage. If there is a if there is a shortage of voltage, we then supply it. If there is over voltage, we then absorb it. It's very important. It's a very important part of the power flows. If you were to talk in terms of like power flows, real power, reactive power, and so forth. So this is your typical transmission uh, uh, station. So in between generation, transmission, and distribution, there will be transformers, there will be substation for either for switching the voltage levels, or and sometimes also these substation are used to also step down voltage. For example, from transmission to the distribution network, we have substation that's then also in place to help with the voltage drop. So one of the important tools when it comes to planning for infrastructure, whether you're designing a new infrastructure or you are managing a new infrastructure, it's system analysis and planning. So there's there are types of analysis, always starting with the load flow analysis, which deals with the normal conditions of the flow of the power or of the flow of the electricity. So if we were to do an electrical engineering course in in one of the modules or units wherever you're based at, you would do electrical protection or electrical protection, yes, or just protection basically. And these are one of the things. It's power systems and protection. These are one of the things that you learn: analysis, load flow analysis, the power flows. So you see, for example, a generation network or a plant is represented using a generator, even though we know it could be more than one generator. It could be, a network of generators. And then obviously transmission line. which we have a vast many transmission line. It could be just a simple line, and then the load as well and so forth. I think you get the idea. So this is called the single line diagram, where we simplify everything on the grid to make it easier to do calculation and also simulation to understand the flows of power and also the voltage and current as well. So these are the basics of the load flow studies. So the normal flow, we call it the steady state condition, where everything is running accordingly. Obviously, there'll be transient states where maybe there'll be a disturbance, there'll be an abrupt in the flow of power and so forth. So it's used to determine the flow of power, voltage, and current in the system under any load condition. So we also look even into overload condition, overload condition, which we try by all means to avoid, because if it's overloaded, the possibilities are, what are the possibilities? We could, damage the insulation, we can damage the generators, overheating, all those things, and that could collapse our grid, and we will not have power for some time. However, we do analyze, or we do also review those scenarios as part of the contingency plans to make sure we don't get there. So these are some of the mathematical analysis that one obviously would then study if they were to go deep into protection and power system. So these are the mathematical analysis. Obviously, you do them uh, as in with your, your normal, not normal, but scientific calculator, your pen, handwritten or hand solved analysis. Um, and then we have simulations where we then, whatever we did mathematically, we then go and test using simulations. So simulations, they sort of also give you like, you know, sort of real time what's happening with whatever you are doing mathematically or hand with your hand, like handwritten. So this is a load flow analysis that was done on ETAP. So there's quite a few softwares, ETAP, there's Silent, now there's Simulink with MATLAB. Um, but Silent and ETAP are the one that are normally used when it comes to load flow analysis, and also Power World as well. So once again, generator by one generator is replaced. This could be a power plant, or honestly, and these are buses that connects generation to transmission. Uh, these are single line, uh, well, we'll say wires, but really they are transmission conductors. And then we have loads, and obviously, if you see on the buses or near the buses that there are percentages which sort of tell us the capacity at which the those buses are running, and also even for voltage as well, we can see, I think it's the following slide, you can see the voltage at what percentages are they running. So uh, this brings the aspects of grid codes. So voltage has to run at a certain percentage, power as well. So with voltage, shouldn't be less than 95%, not more than 105%. And then with power, right above 90% of its capacity. That's nominal, by the way, nominal capacity. So when you design a power system, it's not just a matter of technical component, but there's also code as well that one has to um, uh, abide by. So on the right figure, those are the other results. Obviously, it states whether at a certain point the system is the voltage is under voltage, over voltage, and so forth. And also when it comes to the power as well. This is another example as well. So when we do the mathematical analysis, or when we do the handwriting or the handwritten calculation, uh, we will draw a typical single line diagram. This is what we will draw. And then based on this, we will do the mathematical analysis. And after we've done that, we uh, then go to the simulation where we use obviously the software to redraw it, and then we run the simulation, and then we compare uh, the mathematical analysis with the simulation analysis. One of the important things as well is also the protection of the system. So this is like the basics of when it comes to protection. You'll find that the system has protection zones. So obviously there'll be a protection for the generator, protection for the the transmission, the lines. So the protection zone, obviously they sort of act like a primary protection. They have to detect whatever fault within them. If they don't, then a backup protection zone, which will be a secondary protection, will then react. But the idea is to have the primary uh, protection zone to respond. So they have to be reliable. They have to be selective. Obviously, they have to detect a fault within the zone, not outside the zone, and also they have to be sensitive in terms of like low current fault. They have to be able to detect that. So it's very, very important to have protection in place. As much as we do load analysis, also we have to protect the system as well. And okay, so here the initial load analysis was done for this system, which I just was going over regarding its protection zone. The initial load analysis was done, and then you find that especially at the bottom, the voltage are below 95%. Hence, you in the second slide, or the following slide, we have capacitors. Remember what I said about capacitors? Is that capacitors, they supply the reactive power, right, to compensate for the voltage drop. Yeah. So stability and control, I'll try to be quick. I see the time. Uh, we're quite behind. We're supposed to leave 10 minutes for questions. So I got like 2 minutes to just quickly go over this. So stability and control is very important. As I've mentioned, that we have to keep voltage at a certain level, and so with frequency as well. So frequency plus minus zero 0.5 hertz. So South Africa or Africa, Europe, we synchronize our system 50 hertz, and you'll find in North America and so forth that side is 60 hertz. So we chose 50 hertz. It's quite a long history. It's very interesting, by the way. People came together and then we chose 50 hertz. You can read on it. So everything is synchron, like generators, transformers, like the system is synchronized to operate at 50 hertz. So we only, or rather, it can go by plus minus, go up or down plus minus zero 0.5. If you were to be stricter, plus minus zero 0.2 hertz. So that's what, 49.5 or 49.8 to 50.2 to 50.5 hertz. Once it go beyond or below those limits, then it has to then trigger the protection system to then um to or circuit breakers rather to isolate that the space. This also speak to stability and control. And then this is the distribution network. So after the transmission network, then I think we did see the transmission substation. Now this is a distribution substation. So here we see the transmission line coming in, obviously being processed by lightning arresters from lightning, and then the distribution transformer then lowers the voltage into a voltage that will be able then to supply homes and so forth. This is a distribution network in a nutshell. These are some of the case studies based on our grid in South Africa. Um, so recently we've experienced load shedding, which is different from blackout. So blackout is sort of like um, uh, uncontrolled interruption of power supply. It just goes out. Whereas with load shedding, it's rotational and it's controlled just to make sure. So what happens is that there is so much demand that uh, does not it doesn't match with the supply. So the demand is more than the supply. Hence, we then share load shared, sort of like some load we then disconnect from the grid to make sure we keep the supply and the demand stable to ensure that the frequency is stable and the voltage is stable to ensure everything is stable. Yeah. So these are some of the case studies scenarios. The first one that we ever had was the Natal blackout, and then we thereafter. So back then the grid were separated. So there was a maximum. So it was on maximum demand, and if you look the neighboring grids at the time, it was the transfer system couldn't assist also. So hence in 1973 they then had to integrate all the grids to the grid that we have today, the South African grid. So they were fragmented before then, and now it's one grid. So we are able to help each other in terms of balancing each other. Yeah. And then the next one was the cascade effect at Witbank, where the current transformer failed. If a current transformer fails, it's the one that normally sets boundaries for the protection. If it fails, then there will be misreports of data and we might miss some fault, and that can lead to cascading effect. And then the last one was when two Quebec units, Quebec, our nuclear power station in Cape Town, and Letabo unit, they went out, and it was about 24% national load that we lost blackout. So we've never had a full-on blackout as we've seen in Pakistani, in Spain and so forth. So these are some of the lessons that we can learn from these case studies, and this is where I'll stop to just to make time for questions and whatever information that we would like to share thereafter. Busi, can you please come through?
Thank you very much, Samkelo. That was a very insightful presentation. You can tell that you're a very dedicated academic with the way you just take us through all the different concepts and making sure that we understand. So thank you very much for the presentation. Let me just take control. All right. So we're just gonna make room now for any questions and answers. Are there any questions with regard to the presentation? Let me just check the chats. Okay, let me just see. We've got something from Carol. It reads, I was impressed about the history of electrification sites. Also, I will be downloading the certificate of attendance to show my employer. Another interesting topic was the protection analysis. Thank you very much. So this is more of a comment, but thank you very much, Carol. Are there any questions? Something again here from Christabel. It reads, are there specific generators that are used in conjunction with turbines in power plants? How do you know what type of turbine is to be used in the power plant? Samkelo?
Yo, Christopher, that's an interesting question. So I think it's sort of a multi-layered. The first one is which power plants that employs turbines. So these are your conventional power plants, your synchronous generators, and so forth. That obviously um, employs the rotational movement to generate power. So uh, your thermal, your your wind, your so thermal includes, by the way, include anything to do with heat, employing heat. So anything to do with heat that requires steam turbine. So your fossil fuels, if you look at your coal, your gas, even with nuclear as well. Nuclear is steam, it's thermal, by the way. It employs we didn't cover it, but just to bring to attention, it's also thermal. It employs steam, hence we need steam turbines to act as prime movers to drive the generators. And uh, and then obviously with wind, we employ wind turbines and so forth. And then obviously, if you look at power plants like even bio as well, by the way, because bio we also use, even though we burn wood, we burn waste and all those things, it's still steam to drive the turbines. Whereas if you to look like your solar power plants, they don't require turbines. They're static, you know. Um, so they their sort of connection to the grid is it's converters. It's converters. Then as compared to your rotational or synchronous generators, which its connection, it is transformers, but also generators as well. Yeah.
Thank you very
I'm not
much,
sure if I fully answered
Samkelo.
the question. Yeah.
Christabel, are you answered? Okay. Christabel is happy. Thank you very much. Are there any other questions? All right, there is just a follow-up from Christabel. She says, you have talked about power transmission and grid lines. It is known that there's power losses along the way. How are losses evaluated during transmission, and what are the main contributors to these losses? And are there criteria in place to determine system load demand?
Thank you.
If you can
That's it.
just please address that in just a very short
Thank
manner,
you.
please.
It's an
Yeah.
interesting question. It's a very fully fledged question, I won't lie. So, okay, how losses are evaluated during the transmission line, transmission rather. So, losses basically are heat. It's heat. Okay, so if we were to then go into class now and write an equation, the heat is power, but it's lost power. It's power that is lost. So power is what your I squared times R. I being the current and R being the resistance, which causes the heat, you know. So with transmission line, what we do, we try to reduce current because current is has it contributes the most as compared to resistance. Remember, power that is lost or power in general is I squared R. So if we were to double current and double current, if we were to double this thing a current and uh and resistance, you'll find that the current has the quadrupling factor as compared to just the doubling factor of resistance. So what we do then, we reduce the current to make sure that we don't, you know, or losses or big losses do not occur. I want to go back to the question. Okay. There's so many questions now. So going back there, and then the main contributors to these losses, again, as I mentioned, is the resistance. But obviously, with the AC system, we call it the impedance because it's not just the resistance. Now we have the capacitive, and also the inductive component to the transmission lines. Especially the longer they get, we then also bring that into the picture. Normally, for short distance, we only uh, use resistance and current to evaluate losses, but over longer distances, we then add the capacitive and inductive components to it. Yeah.
All right. Thank you, Samkelo. There are quite a few more questions, so let's just see if we can just get through them quickly. So we've got something from Tobile. It reads, for someone wanting to deepen their understanding of power system protection, what key topics or resources would you recommend?
Well, I would love to say come to ECST. You're gonna learn about it here at ECST. So, power system protection, obviously, you will have to understand the fundamentals of power system. You also have to understand electrical circuit theory. So those are some of the key topics or the basics that can build you up, prepare you for power system protection because it's simply electrical circuits, power system. Now, obviously, we are analyzing fault disturbances in the system. Yeah. And then the last one, um, which power system design software can student learn that is also used at professional level by companies like ESCOM. So
Mhm.
Dig Silent is the one as I've mentioned. Here we saw ETAP. Dig Silent is the one. Even at ESCOM, engineers will tell you Dig Silent, even though at ESCOM, uh, because if you look at the our national electricity plan, it was the PSSE. So please, PSSE, please check that. I think it's Power System Simulator for Engineers. It's sort of like professional level, like most companies use that one. And also ESCOM does, but they also use Dig Silence. So they recommend, for example, someone who wants to, example, join ESCOM as a graduate or as an engineer in training, they will ask you then, do you have experience in Dig Silent? If you have that experience, then you can use those professional software that they use as PSSE. Please do search that one.
There's one more, Samgelo, if we can just cover it quickly, please. It's from
Mm-hmm.
Doreen. It says, what are your opinions on synchronous condenser to supply inertia
Ooh,
whilst our coal-fired plants are set for decommissioning in the future? Do you think a complete system analysis needs to be done to accommodate protection settings within the transmission and distribution network?
I say come to our next webinar. That's with my question because we will speak about
Okay.
that, the integration of renewables into the power system. But in a nutshell, um, we do need inertia. If we're decommissioning so many power plants, which sort of produce or provide this inertia. So inertia is sort of like uh, a resistance to change. So it helps us to sort of keep the frequency, within the limit. Once we don't have that, what happens to Spain? What happens to part of Florida in America? What happens to Pakistan? It will happen to us. There will be a collapse in a couple of seconds because there isn't much inertia. So we do need synchronous condensers. And if you just go read the Transmission Development Plan 2024, I think it's the latest one. There is sort of like a chapter where they speak about the synchronous condensers, how they'll deploy that, and I'll also touch on it. We will also touch on it on our following webinars. So yeah.
All right, thank you very much. That is all for the question and answer session. Like Mr. Nene has said, if there are any more questions or if you're just interested in learning more and hearing more from him, just please join our next webinars where there will be quite a few. Just also for noting, Um, if you're also wanting to join at the college, we are offering our Bachelor of Engineering Technology in Electrical Engineering. Our next intake will be in July with classes starting in August. So please, if you are interested, please just visit our website. I will put up our contact details at the end of the presentations, but just please visit our website and just feel free to complete an application form. With our upcoming webinars, we've got another one on the 4th of March. That's the integration of renewables into the power systems. So you'll get to see Samkelo again and just get to hear more from him. We also have a virtual information session that will be hosted on the 18th of March. Again, just please visit our socials, visit our website, and just register for these, please. And as promised, this is the certificate of attendance. This is the link and the QR code. If you can just please just take a moment to copy these and scan them, because this is where you will be getting your certificate of attendance. So thank you once again for joining. I'll just leave this on just for a few seconds so you guys can just again copy and scan the QR code. And also just for noting, these slides will be shared with you. So if you do not get a chance to just copy this, do not despair. We will be sharing the slides with you. So you can just do that again in your free time. All right, so these are contact details, contact and information resources. Please visit our website, learn more, and just check what we are offering. And again, a reminder that our next intake for our Bachelor of Engineering Technology in Electrical Engineering will be July with classes starting in August. So please just inform all your friends, inform the parents, whoever has joined this webinar, just please feel free to spread the word. Thanks again for joining, and we will see you again in the next webinar.
Thanks so much.
Thank you. Bye.
Thank you. Bye bye.